This last section about describing data is going to go more into how we display and then explore the data once it's been displayed. Going back to our discussion of measures of position, one of the things that we look at is the location of a percentile. You know, we've talked about standard deviation, and it's typically the most widely used measure of dispersion. But another method of describing dispersion is with a measure of location, where we have the formula of a percentile shown here on the screen, where P is going to represent the percentile, N is the number of values in the data set. So to find the quartiles, you're going to divide it into four equal parts, where you would use Q1 being 25, and then the third quartile we would have 75%, and the median is going to be the 50th percentile. The data has to be ordered from smallest to largest for us to do this. Quartiles, deciles, and percentiles are really commonly used as a measure of location. 25% of the data is going to be less than the first percent quartile. 50% of the data is going to be less than the second quartile. 75% of the data will be less than the third quartile. If we're looking at the interquartile range, typically that's going to cover what that is that's the difference between the third quartile and the second quartile. So that's going to cover the middle 50% of the data. And that's going to be easily seen in what we call a box plot. And so that's going to graphically show our quartiles that we have. And so we need to know our minimum value, our first quartile, our median, our third quartile, and our maximum quartile. So those are going to be shown in our boxes. So we begin by drawing a number line that accommodates the minimum and the maximum values. And then we draw a vertical line above the median, Q1 and Q3. And then we enclose these regions between the first and third quartiles, creating a box. Next, we're going to draw dotted line segments from the third quartile to the largest value, and then from the first quartile to the smallest value. Sometimes these are also called box and whisker plots. And so what this is going to do is it's going to show the largest 25% and the smallest 25%. And then, as I said earlier, the interquartile range is going to be that middle 50% of your data. So here's an example of a box plot, and here we see that the box plot of this data shows us that this data is positively skewed, since our dashed lines to the right of the box from 22 minutes to 30 minutes is going to be longer than the dashed line to the left of the box from 15 minutes to 13 minutes. And since the median is not in the center of the box, we can also see that our data isn't completely symmetrical. There are four common shapes of the data that we see here. So symmetric is when your mean and your median are equal. Positively skewed or skewed to the right is going to be when your mean is greater than your median. Negatively skewed data is going to be when your median is greater than your mean. And if you have bimodal data, that's going to have a shape where you have two or more peaks that indicate two or more populations might have been combined in that one measure. Skewness has a value called the coefficient of skewness, and that's going to be that quantifiable value of the measure of the symmetry and the distribution. So Professor Carl Pearson developed this simple formula for calculating skewness, which is based on the difference between the mean and the median. But if you look in other textbooks or whatnot, you can have a calculation for skewness, but it's not the Pearson coefficient. So oftentimes it'll be using the formula up top that you see here. These values will range from -3 to +3, which is similar to what we talked about in our empirical rule. Values that fall within -3 and +3 standard deviations are typically not considered to be outliers. But here, you're using that value to figure out skewness. So if you have a -3 value for skewness, you have a considerable amount of negative skewness. Um, if you have a value of like 1.63, that's a moderate amount of positive skewness. And then if your skewness is 0, that means your distribution is symmetrical. So you can look at different kinds of skewness using histograms. You can also use it looking at some of the other graphical displays that we've already talked about. But if we look at this first chart here that's symmetric, you see that there's 0 skewness because our mean, our median, and our mode are all the same value. Here, if we look at our positively skewed, that's going to be the case where our mode is less than our median, which is less than our mean, and it has a tail on the right side. So that moderately right skewed is called a positive skew. And then we also have our chart where we see our mean is less than our median, which is less than our mode. And that's going to be negatively skewed with the tail on the left. So also, if the distribution is highly skewed, this is going to be indicative that the mean is probably not going to be a representative measure of the central tendency of the data, and you might want to consider using the median or mode when you're discussing that. When we're looking at scatter diagrams, it's a graphical representation of the relationship between two quantitative variables. When you make a scatter graph, you're going to scale one of the variables. The independent variable is going to be on the horizontal axis, and the dependent variable is going to be on the vertical axis. The general pattern of the plotted points will suggest the overall relationship between your variables. And so we can make what's called a trend line to look at an approximation of the relationship. So here, there's a positive relationship between age of the buses and their maintenance costs. So we see as the buses increase in age, the maintenance cost is also going to increase. This next group we have a negative relationship. So this is showing that as my odometer readings increase, my auction price of my vehicle is going to go down. And then here, our final graph is showing that there's really no relationship between salary and the height of our supervisors. Another graphical representation that we're going to talk about is called a contingency table. Sometimes they're also called cross-tabulation tables, but basically that's a summary of data for two variables. So they can be used when one variable is categorical and the other one's quantitative. You can use them when both of them are categorical, or sometimes you can use them when they're both quantitative. But the top and left margin labels define the classes for your two variables. If your data is interval or ratio level, it's going to need to be converted to nominal or ordinal before the crosstab is useful. So here we have an example of a contingency table. We're going back to looking at our home prices for the different floor plans offered by Finger Lake Homes. And so here over here we've got our quantitative variable, which is going to be our price range that we've divided into two classes or bins of being above or below $250,000. We have a categorical variable, which are the 4 different kinds of floor plans or home styles offered by Finger Lake Homes. Here we've got our frequency distribution for our price range variable. And then down here across the bottom we have the frequency distribution for the home style variable. And then the individual cells in here are going to tell me how many observations meet the criteria for both categories. So in summary, we have data, and data can be classified as either categorical data or quantitative data. Categorical data can be displayed in different kinds of tables, from relatively to frequency distribution, relative frequency distributions, percent frequency distributions, and contingency tables. Graphical displays include bar charts, pie charts, side-by-side bar charts, and stacked bar charts. But when we have quantitative data, the tabular displays are basically the same ones that we had before, right? So we have frequency distributions, relative frequency distribution, percent frequency distribution, but now we also have the cumulative frequency distributions as well. Graphical displays for quantitative data include dot plots, histograms, stem and leaf displays, as well as scatter diagrams.